Hello. Hello.
Hello.
Hi.
Hi. Yeah.
Nice to meet you. I'm Hagar.
Okay. Nice to meet you. Okay.
So, yeah, so I didn't get the hours wrong, right? We officially start in 1 hour.
Yeah, right. So can I test the maybe this. Is this okay?
Yeah, it looks good. There's also a live stream on YouTube. Let's see if it's working fine. Hello, hey.
Hi.
Hi, sorry. How do you pronounce your name?
Yutaro.
Yutaro.
Yutaro Shoji. Yes.
Yutaro. Is it okay if I'll take over the screen share to put on the counter?
Yeah, of course.
Okay.
Okay, yeah.
Okay, do you see it?
Yeah, I can
Okay.
see the counter.
Okay.
Yeah.
This shouldn't be here. Just a second.
Hello, can you hear me? Hey, Hagar?
Hey, what's up?
Good. How you doing?
Pretty well, considering.
Considering, no, great.
I sent you the YouTube link.
Yeah, I saw it. I don't know who to send it to. Do we need to send it to everybody, or doesn't? I mean, we have 300 spots in the Zoom. All right. Yutaro?
Hi.
Hey, how you doing?
Hi. I'm very good.
Yutaro, you're coming to Jerusalem?
Yeah, and in the September, if the
Nice.
coronavirus is, yeah.
You got faculty?
Sorry?
Are you coming
you mean?
as faculty? Are you coming as a faculty?
Connection is not so good.
Ah, okay. I hope we can. Can you hear me now? It's better?
Yeah, it's better, yeah.
Okay. Are you coming as faculty?
Just a postdoc. Yeah.
Ah, okay.
Yeah.
And you work with, you're going to work with Yonit and Eric?
Yeah.
Ah, nice. They coming today? No? Okay.
Maybe.
All right. Did you test everything is okay? You can upload your screen and all is well, or how are you doing this? You're sharing Hagar's screen?
No, my screen is just for the countdown.
Okay.
I'll stop sharing.
Good.
I'll stop sharing my screen.
You already stopped?
Yeah.
Okay.
Okay, that looks good.
Hello, Yutaro. Thanks for joining.
Hi, hello.
It's Matteo here.
Wow, nice
and thanks, Hagar, for this wonderful organization.
Yeah, I'm sorry about the coffee and the cookies, but...
I have coffee. No cookies, it's Passover. We're not allowed.
Well, but maybe at the end of the talk, we can, I can search on Google some nice image of coffee and cookie, and we can put this, can share my screen at the end of the talk.
It's super kind of you.
If you're not worried that we are going to live stream it to the entire world, everything is fine. All right. Did anybody send it in some wild distribution list outside Xenon? Xenon Darwin? I said you can invite people if you want, but I only invited a few.
I have not circulated the email outside this list on a public, so I have not put on any public website.
Ah, no, not a website. Just wondering if somebody sent to LZ collaborators or the Panda guys. Okay, maybe we're not as nice as we said we are. Tara, do you is your connection good now with hearing what everybody's saying, etc.?
Yeah, it seems good.
Okay, good. I think I have like the lines on your, it tells me what's your connection style, and it's good.
What do you mean?
No, it seems that your connection is doing well.
Yeah, I think connection is yeah, nice. I think.
Okay. You work now with Shingo and Kentaro, I see. You now work with Shingo and Kentaro.
Yeah, Kentaro, yes, yeah.
Okay, that would be good to know. All right.
Yes, we have just started some collaboration. Yeah, just doing to do some proof of principle experiment for the Migdal effect.
Okay. Shingo was one of the lead authors on the Xenon Migdal paper.
Yeah, and he's also in the Nagoya University here. So I sometimes met him, but the building is a little bit far from here. But basically, we are in the same institute. So.
Oh, I see Shingo is here. But in Japan, you're not in lockdown.
Not locked down.
Well, I think almost everybody else is. Okay.
So Rennie, you are, how is it at Stony Brook?
I'm in Stony Brook, yes.
Right, so how is it there actually? It's just, you're all at home as well, right?
Yeah, it's kind of leveling everything because nobody is going to work. So, and the home here is actually nicer. Yeah, I still have hopes. So I think in a few weeks, the United States at least will start to open.
Yeah, so in Switzerland it might start after April 26th. That's what we know now. So we'll see. Yeah.
That's, I mean, compared to what we've been through, this is really nearby.
Yeah.
I hope that this will be.
I mean, it will be a gradual opening, obviously, right? So
yeah.
The classes will stay online until the end of May, but hopefully we, people working in labs and so on, that we can start going back, but definitely not the undergraduates yet.
Yeah. Well, it's probably going to be similar here. I don't know. Travel is going to be very limited for a long time, though. Good for the planet.
Right.
Yeah. Well, I think we have almost 50 people and we're 1 minute after time. Give it another minute. And then we will start. Yutaro, I asked, is it okay with you that we record?
Yeah, you can record.
Okay. Okay.
Okay.
We would record anyway, but now that you agree, it's even nicer. So, okay. What is the rate of added participant at which we start talking? Similar to the virus case.
I think that there was a drastic increase in the last couple of minutes, and now we are reaching the peak, I guess.
Well, I hope it's going to be kind of a plateau.
Well,
No?
you can increase.
Maybe you can start anyway, because some of us have other meetings at 4. So.
All right. We will.
Really nice. Yeah.
Okay. So we are very happy to have it's a Darwin seminar, but actually we invite people from all over. I didn't look where you come from. By Dr. Yutaro Shoji. Yutaro did his PhD in Tohoku University with Masahiro Yamaguchi, Professor Masahiro Yamaguchi, and is now an assistant professor at the Kobayashi Masakawa Institute for the Origin of Particle Physics in the Universe, Meiji, Japan, and will join the Hebrew University in Jerusalem starting this fall. Hopefully everything will be good. And we're very happy to have him here talk about the Migdal effects and some new ideas on the paper that was very innovative, and he was one of the authors of it. So Yutaro, go on, and I will stop talking.
Thank you very much after attending this seminar. Maybe some of you are early in the morning. So today's topic is the Migdal effect, and this work is actually 2 years. We did it in 2 years ago, and it's in collaboration with Masahiro Ibe, Bakutaka Nakano, and Kazumi Suzuki. And currently, we are also working with some experimentalists, Shingo Kazama, Kentaro Michi, and Kiseki Nakamura. And so, let me start the, So, So maybe I heard that you are all the specialists of the dark matter, so let me skip the beautiful pictures of galaxies. And so let me start with the direct detection. So just the direct detection, it's just waiting for the dark matter to hit the atom, and just measure the recoil energy. And then the dark matter velocity is just calculated just using the computer. So this is just a simulation, but it's roughly, the dark matter roughly has 200 kilometers per second, and it's roughly Maxwellian distribution of the velocity. And but there is a certain cutoff for the velocity, because if it's faster than this, then it's just go away from our galaxy. So let me just use 200 kilometers per second and 550 kilometers per second for just a presentation. And of course, the Earth is moving, so if you consider the motion of the Earth, then you can add the additional 200 kilometers per second. So what we usually observe is the elastic scattering of the dark matter with the atom. And it's actually almost all of the scattering is elastic. As I will explain later, but actually this elastic assumption of the elastic scattering is very nice. And if the dark matter scatters with the dark matter elastically, atom elastically, then the its energy deposit is just I plot here. So it's the dark matter mass versus the recoil energy. Plot the recoil energy is the kinetic energy of the recoil atom. So for the if it just shows that the dark matter mass becomes smaller than the recoil mass becomes smaller very, very fast. So let me just assume that the this detector can detect the recoil energy of the 2 keV. Then you can see, maybe you can see that it's, if the dark matter mass is say less than a few GeV, then the signal cannot go over this threshold, and then we cannot observe the signal. So that's the elastic case, and actually, in principle, the dark matter itself has a very much larger kinetic energy that is larger than this recoil energy. So the question is that whether we can use this energy and observe that this dark matter within this totally using this dark matter kinetic energy. So that's the question. So basically, we can do it. Maybe you as you learn in the undergrad. So let me assume that just perfectly inelastic scattering. Then because in the inelastic scattering and in perfectly inelastic scattering, the dark matter and the atom are at rest at the center of the mass plane. So it just absorbs almost all of the kinetic energy of the dark matter. So I just plot the total energy that we can use and the dark matter mass. So as you can see that we can use much large energy for the inelastic case. So that's why we consider the inelastic case, inelastic scattering for especially for the light dark matter. So this delta E is basically the energy released in the some inelastic scattering. We can consider the atomic excitation or some Bremsstrahlung processes because this energy is roughly keV region. So it's a very nice place to consider the atomic excitation. And after the atomic is excited or ionized, finally it recombine or relax to the ground state. So in that process, they emit the photon or electron. So basically, this is kind of the photon or electron injection inside the detector. So here, that brings us another enhancement factor. So for the just recoil energy, the kinetic energy of the recoil atom is most a large part of that energy is converted to the phonon energy. That is, you can easily imagine because just the atom hit the other atoms and it just heat up the system. And some of the scattering is inelastic, and that just causes take over some electrons and excite the atom. And then finally that gives scintillation light. But for the delta E, it's just emit the photon and the electrons that directly excite the atom. So almost 100% of that energy is just going to the electric excitation, and that finally goes to the scintillation light. So that means that the corresponding compared with the recoil energy, the delta E has 5 times efficient in this sense. So let me just put the factor Q and L that is usually called quantum factor to the recoil energy that is I estimate 0.15, and then plus delta E. So this is the total of detectable energy. So now the inelastic scattering, this is totally perfectly inelastic case. But the inelastic case has a very good, nice, great advantage of detecting light dark matter. There is a very huge enhancement of this energy that we can use. So that's why we consider the inelastic scattering, and then that's the interaction. So let me next explain what is the Migdal effect. That is, in this is not first not connected to the dark matter directly experiment, but just the Migdal. What is the Migdal effect? And then I will formulate the Migdal effect in the didactic direction experiment. And there we need some electron wave functions, so I will show how we obtain these functions. And I will show some event rate for the Migdal with the Migdal effect. And then some of you may also interested in the neutrino from this the coherent neutrino nuclear scattering. So I will explain that. And then I explain the counterpart of the Migdal effect. There is another inelastic scattering that is a Bremst line. So I compare them. Then I will say some neutron source experiments. And there is some more. So let me just start with the Migdal effect. So interestingly, it's in the textbook of the Lambda waves, and it's problem number 2. So basically, in principle, bachelor course student can solve this problem. So the problem is just like this. So let me just prepare atom, the ground state atom, and then we assume that they just get an impulse at the t equals 0. Then problem is that what's happening to the electrons. Some of the electron may be excited, some of the electron may be ionized, but the problem is what is the probability to have that state? So there is a very nice, very clever and a tricky solution, and that is this. So we prepared the electron wave function at the lab flame, but we can go to the left flame of the nucleus. Then what happens is that the nucleus is of course at rest, but the surrounding electrons are moving in this direction. Oh, yeah. So basically, we can calculate that state because that is just a shift operator for the momentum. So we just multiply the shift operator for all of these electrons, then that is the this electron wave function. So once we get this wave function, then the probability can be easily calculated. Because that's just we re-expand this state with the energy eigenvalue at the rest of lambda nucleus. This is the usual atomic wave function, including the excited states. So the probability is just the coefficient squared. So this is just simple quantum mechanics. So, and it's quantum mechanics. It's a very very nice to see the time evolution. We know the Hamiltonian, and we just constructed the energy the state to its energy eigenstate, so we can calculate the time evolution. So this says the this I will show the movie, but this is the at rest of lambda nucleus, and the nucleus is at the center of this figure. So let me just start. This is the actually the electron wave function. So it's actually this nucleus is moving in the toward the right bottom direction, and the electrons are left behind. So actually, yeah, things are very going well. So actually, we are really calculating the evolution of the electron after the collision. So basically, this movie is assumed a very large energy momentum transfer. So actually, in the usual dark matter scattering, this is too large. So this is just presentation. When the momentum transfer is small, then the electrons emitted also the forward region. It's both the forward region and the backward region. It's just the motion of the nucleus can be understood as just a dipole oscillation. So just the electrons are emitted the forward and the backward. And that's the what's happening in the dark matter case. So this effect has been the application to the dark matter direct detection has been discussed for a long time. Maybe it's started from 2004 by Migdal and Julie, and there is a series of papers by them, and they also, I think this is a Darwin group, also calculated for NA and I. So and what we have done is we brush up the discussion, and also we have considered the other atoms. So let me formulate. Actually, the formulation is not so difficult. So basically, this is quantum mechanics. Not so you don't need to know the field theory or something like string difficult theory. This is just of quantum mechanics. So what we have to know is just a transition amplitude. That at the first Lucas mentioned, that is the sandwich of the interaction of the nuclear dark matter and nucleon with some energy eigenstates. So then just calculate this final the H int times I is the linear combination of the final state. So there we can just get the probability. So that's just a usual case, but in our case, there is one difficulty that is actually the plane wave for the atom. So for the dark matter, we have some plane wave that is the eigenstate of the momentum and energy, so we can use that for the dark matter. But for the atom, it's not so easy to make the plane wave of the atom. So let me just show you how we make it. So let me just first prepare the plane wave of the nucleus. So that's we consider that a point-like particle, so we can just it's ordinary plane wave for the nucleus. Then we a direct product, take a direct product of the nucleus and the electron wave function. But this is not, of course, this is not good because the electron are at the origin of some coordinate and it has zero velocity. So at least we need to move, give some velocity to this electron. So we put this momentum shift operator, then these electrons are moving in the same velocity, with the same velocity with the nucleus. But it's not so still good because you can find a nucleus maybe around here because this is plane wave, so you can the nucleus can be everywhere. So, but the electrons are still at some origin. So it's just a break of the atom. So so we can multiply this operator finally. And this operator, what this means that the xn is operate to the nucleus wave function, plane wave, and then find where the nucleus is. Then PE is actually the shift operator of the electrons, special shift of the operator. So if you find the nucleus here, then this shift operator just move this electron wave function to the same position. And this is very easy to understand. And actually, this gives a very nice eigenstate of energy eigenstate. So we use this this state for the atom wave, plane wave. So once we get the states, then what we have to do is just take a square. And then the probability is given by the this transition amplitude squared times some energy conservation delta function. And then assuming the contact interaction, of course, you can use non-contact interaction as well, but let me just assume the contact interaction. Then what we get is a usual formula of the cross-section times Migdal factor. Except for the Migdal factor, this is completely the same as the nucleus atomic scattering. And this Migdal factor, maybe if you remember this factor, then this is the same as I explained before. That this is the completely what I explained in the the Migdal section. So that's the formulation, and anyhow we need wave functions for the electrons. And we use the single configuration Dirac-Hartree-Fock method. And this is very basic way of getting the wave functions. So we first asking some mean field and solve the wave functions of the electrons one by one, and they construct all of the electron wave function like this, and then calculate mean field again using this wave function. Then we calculate the wave function again. So iterating this, finally we reach some self-consistent solution. That is the wave function in this approximation. So what we prepare is, of course, the ground state is used for the initial state. So we prepare the initial ground state. And we also prepare single electron excited states and the single electron ionized states. Basically, we can consider the 2 electron or 3 electron excited states, but actually layer 2 is very small, so that we can use only the single electron excited states. So these are the final states. To get the wave functions, we use the public codes called the flexible atomic code. And you can get the wave function with some you need some modification, but actually basically you can get the wave function from this code. And this is not only for the calculation of the single configuration Dirac-Hartley Fock, but it also calculates large configuration, or it also calculates some additional correction. But we only use the single configuration, the faster approximation, because the more accurate method just complicates the calculation, and but in principle we can use more good atomic electron wave functions. And once we get the electron wave functions, we can calculate the Migdal factor. And here we have additional approximation. It's expand this exponential of minus IQX, just QX, just the first approximation. So yeah. So this table shows the probability. So this is the initial state. Then this is the final state. So this is the bound state. This is the ionized state. And you can just ignore this outer shell, because in the liquid xenon, this outer shell is easily affected by other atoms. So you can just ignore this outer shells. And then if you see the probability, it's kind of -3 or -4 or 5. So it means that actually when you can see the events from elastic scattering, then you don't need to care about the inelastic scattering. That is small, that probability is very small. But this Migdal effect becomes important when you cannot observe the elastic events. That if that is below the energy threshold, then you cannot observe that event. But for the inelastic case, as I explained in the introduction, it can use almost all of the initial incident dark matter kinetic energy, so that it can still excite atom, and it can still give the observable signal. So that's the point. And actually the uncertainty, I'm often asked, but actually it's a little difficult to calculate the uncertainty And for the energy, because energy is easily measured, so energy uncertainty of this energy, this is calculated by using this wave functions. The same the algorithm with the observed one with accuracy of 20%. But for the probability, it may be safe to consider there is some order one uncertainty also, because we do not consider the multi-configuration Dirac-Hartree or even here we approximate the QX, the first order in the QX, and also the other atoms can easily affect the wave functions, especially the outer shell, but I don't know how it affected this so quantitatively. So that's the calculation. And we can also calculate the spectrum of the emitted electron wave, emitted electron. So, yeah, basically this. There's some strange structures come from the shape of the wave function. So don't just see. And then for the maybe the ionization data is most important for the dark matter detection. So we prepare some ionization data in the archive page, so you can freely download this data. The data structure is not so complicated; it's just list the quantum number and the ionization probability, and just two things that we need to care is that first, this is the momentum transfer, the momentum of electron at rest from the nucleus, that is the QE. And the QE is 1 equal 1 EV is used in the calculation. And if you use the different energy transfer, then you need to multiply QE squared in the electron unit. And actually, we put 2 pi here. That sometimes we also forget. So, but please don't forget that this is divided by 2 pi. You need additional 1 over 2 pi. This is just convention. So let me go to the event rate. So this is the status in 2017 because this is when we published our paper. So currently that these stars are excluded like quest 3 and the dark side 50. But let me use these 1 and 2 points shown here. So the point 1 is a rather large dark matter mass, but the cross section is small. And then we show the detectable energy, the KEDE electron equivalent, and the event rate. And then, for example, let me assume that energy threshold for the detector is 0.3 KDE. Then this black line, what this shaded region is the atomic recoil, that without the Migdal effect. And it's just not so, just boundary of the threshold. So let me assume that it's not, it cannot be seen. Then we can observe with the Migdal effect. So then, as you can see, the this green and the blue and red curves for with the Migdal effect, or just energy comes from the excitation or ionization data. And this N is the principal quantum number of the initial electron. So this N equals 3 comes from the just a little inner shell. And then maybe you can ignore the n equal 5 because it's, as I said, it's affected by the other atoms. But so let me just sum up, integrate just only this green region. Then it gives a few events for 10 to the 5th kilogram base. It's maybe enough. And for the 0.2, this is maybe interesting. It's 0.5 GeV dark matter mass, so it's very light. And but at that time, at least, the 10 to the minus 36 centimeters squared is allowed. It's very large cross section, so that the event number is enough. So actually, because dark matter is light, it cannot create events that because the kinematics. But Migdal effect doesn't care. So actually, Migdal effect still gives enough events. Just integrating over this green region gives 100 events for 10 to the 5th kilogram days. So that's the calculation. So let me just go to the neutrinos from the sun. So basically, the formulation is completely the same. Actually, the multiplying the Migdal factor is enough. Then the other things are the same as the usual calculation of this neutrino nucleus scattering. And then the target is the solar neutrino, but let me just concentrate on the largest two, the TP solar neutrino and the boron 8 solar neutrino. So PP case, that's actually like this. So NR is the same as AR, but actually it's just just an ordinary recoil without Migdal. And for the Migdal events, it's just touching the 40-ton kV, but not so large. But for the boron 8 case, actually it will give some events in about for the 14-ton. So it's maybe a few events, I think, only from the middle. So that's the
sorry, can I ask
for,
a short question, or only afterwards?
I think you can. Yeah.
Yeah, I'm just wondering. Sorry, I'm just wondering why you take this kVEE threshold of 0.3 kV that hasn't been reached yet, and probably it's very hard to reach in a detector, right? I mean, we haven't, or what's the motivation, or is it just a number? So yeah.
Just I don't know the detector's threshold for it. I just I just use the threshold for the X mass. So. But actually, I'm sure that some different growth gives different energy threshold and
Okay, so it's just okay. Good. Yeah, thanks.
You can put your line somewhere. Yeah.
Actually, I have also one question on this slide.
Okay.
So in that energy region, we have PP electron scattering. So even though you think that we can see it, this signal?
Sorry?
The PP solar neutrino, you have electron scattering on xenon. So those signals will be covered by the PP.
Electron scattering.
Right.
Yeah. Actually, I didn't put the line, but maybe
It is about 10 to the minus 5. Yes, about 10 to the minus 5.
Okay.
So.
Then maybe that's maybe not much. Yeah.
I guess here he only considers nuclear recoils. That's why. But yes, I mean clearly the neutrino electron scattering rate will be higher.
Yeah. Right. That's possible, yeah.
Okay, let's continue.
Okay, so let me go to the another possibility, the Brahms strand. So actually, this effect is very actually in the actually it's quite similar to the Migdal effect. It's after the heating the nucleus, it's just move, but actually it's screened by the electrons. So outside of the electron, they cannot know what's happening in the center of the electrons. But the electrons can feel what's happening in the center. So it's first excited, then it's just it emits the photon afterwards. And this intermediate state can be virtual. And in their calculation, there is a virtual. And so if we compare this screened Brahms-Planck process with Migdal effect, then actually it's very similar. The Brahms-Planck is kind of an off-shell Migdal effect. So that's also means that the Brahms-Planck, so they need alpha. So the cross section is like this for the Brahms-Planck. It's just like this, and the Migdal effect is just like this. And then we compare if we compare and the difference is this red part. So once, as I said, this is the Brahms-Planck is proportional to alpha, and the Migdal effect is proportional to the just excitation, ionization probability. So that's the difference. And let me just plot these two factors. That gives the difference. And then this factor, interestingly, gives the only this factor depends only on the photon energy omega or the electron energy. So actually, we can plot this like this. So, and the delta E is basically for the Brahms-Planck case, it's omega, and we consider the unscreened case. That means that the emitted photon is energetic, so that we can ignore the effect of the screening by the electrons. So it can be seen like this photon is emitted from the nucleus. So, and then it's actually inversely proportional to omega. And then for the Migdal effect, it's shown in this lines. This comes from the H shell. So, and for the light dark matter detection case, the important range is just limited in around here. So at least it should be larger than some kV or some point, some kV. I don't know whether it depends on the threshold of the detector, but somewhere there. And then if the energy transfer is very large, then you don't need to consider the Migdal.
Can I ask a very quick question? So this factor is the ratio between the two, but which one is on top? I mean, it's, if I understand it right, it's the Migdal effect that is larger, right?
I just plotting this is this line, and it's just 1 over kV, so 1 over omega. So it's just plotting only this factor.
Okay, Sorry, I misunderstood. Thanks.
It's not a ratio of something, but it's just a Brehm-Strang is just this, and the Migdal is the other line.
Okay, thanks. So basically, the Migdal effect is always bigger than this Brehm-Strang.
Yeah, in the important range, yes.
Garo, just quickly, the n equals 1 and n equals 2 are typically not detectable energies eventually. So we're only looking at the n equals 3, 4, and 5 to compare with the. And which one is this delta E exactly? This is the eventual energy of the electron.
Delta E is actually the sum of the for the Migdal effect. It's the sum of the binding energy plus the electron energy, because the just after the emitting electron, it emits X-ray or some electrons, and we observe the both of the characteristic X-ray and the emitted electron. So delta is sum of these in the Migdal case. The brightness
this is the observable.
Just a photon energy. It's yeah. It's say, for example, if this n equals 3, 4, 5 case, I think it's kV range photon. So it's and I think it's energetic enough.
Okay, thank you.
For the outer range, it's electron volt, so it's gonna be seen, but in inner states, it's kV or 10 kV. Most inner shell, it's I remember 30 kV.
Oh, okay.
Yeah.
Okay, that's something.
Yeah. And then if this delta is too large, then you should better to observe elastic scattering. So that's why we limited on this range. In this range, the Migdal effect becomes dominant and also detectable. But in this range, fortunately or unfortunately, Brehm-Strang is rather smaller than the Migdal effect. So yeah. That's why the maybe the both collaboration, maybe the some of you calculated this figure, but that's why the Migdal effect has a better sensitivity in the dark matter, light dark matter detection. So yeah, that's the comparison. And let me just go to how to prove the this effect with using a neutron source. And then naively, it's a little difficult. First of all, I'm just showing the instant neutron energy versus the event rate figure with some fixed flux of the neutrons, 10 to the 3 centimeter squared per second. And for let me just this is for the 0.3 kV detector threshold. But for this case, actually, Migdal effect becomes dominant when the instant neutron energy is less than, say, the 6 kV. It's a little small kinetic energy for the neutron. Otherwise, the atomic recoil is much probable, so that the Migdal effect is completely hidden. So there are two options. One is that you prepare a slow neutron source and you can do it, or you can do some event selection with using a rather large neutron kinetic energy. But I have two options to overcome this difficulty. One is actually I come up with day before yesterday, so this is completely preliminary. So, but let me explain. So, actually, as I explained in the introduction, elastic scattering is very ineffective. I mean, it's just energy conversion rate is very bad. So if we increase the energy threshold, this atomic recoil event just disappears. This is just this end here, and here and here comes from the kinematics. So if the threshold is larger than with this incident neutron energy, it cannot exceed this threshold. So this event, just all of this event shift to the right. Then of course
Excuse me, I hate to interrupt, but I think this is exactly what people here would be interested in. The calculation you do here, you take an energy threshold and you calculate rates. And the question is, do you take the threshold translated to, let's say, detected quantas like photons and electrons, and then actually hold it back, or do you do it as a straight line in energy?
Actually,
I assume.
We fixed the this quantum factor to 0.15. Maybe I remember it depends on the energy, but idea is just this.
So it's a
I think
question
that answers
about
your question, Rennie. With it's a delta response.
It's a delta in energy.
Right.
Okay.
Delta in energy. Okay, it's a delta function, but actually, if you have some width, then you just integrate with multiplying this. So it's easy to see.
Okay, this will probably make it less marked in the rate plot, because you will have events spilling over to the detected area.
So this would be a detector with the infinite energy resolution.
Well, to detect the energy, not the quantum. Okay, but no, it's interesting. I don't want to interrupt.
And just what I want to say is that if you increase the energy threshold, then you cannot observe the atomic recoil. Just very simple. But the Migdal effect, as I said in the introduction, it's inelastic, so we can use the energy of the neutron, fully use the energy of the neutron. So it's kind of 100 keV, so there are plenty of energy. So we can excite the atom. But of course, we cut some lower energy region, so the rate is of course suppressed. So, but it's not so bad. I think it's just 100 times smaller. But still, it seems that for kilogram per day, it's more than 1,000. So, if I did some mistakes, but that is one option. And another thing is I'm currently discussing with experimental people that they're using the gas detector. The good point in the gas detector is that it's dilute. So if the neutron hit the atom, and let me just assume that the most inner electrons are excited, so its binding energy is kind of 30 keV. So once it's the inner electron is emitted, then it can emit the characteristic X-ray. And because the gas detector is dilute, the X-ray can travel on the 5 centimeter or so. for this setup. So then for the gas detector, we will observe the two clusters of the some events simultaneously, almost simultaneously. So we using some 2D detector and the time measure the time, then they actually we can separate these two, and then we use that for the image selection. That is the idea, and we are now working with some background explanation also. That is actually the current situation. So let me summarize. So first of all, the most important thing we see is that the inelastic scattering has a very great advantage in absorbing the kinetic energy of the dark matter, light dark matter. And they increase the sensitivity of scintillation detectors in the low mass range. And the Migdal effect is one of the indirect, not in the elastic scattering. In elastic scattering, and it's just excite atom or ionize the atom. And as I said, the probability is very small. So if you consider some usual atomic recall event, then you don't need to be considered. But if you cannot observe that event, you need to, you can consider this process and fully use the dark matter kinetic energy. And then what we have done is we reformulated the Migdal effect, and then we have shown that actually sub-GeV dark matter can be observed even with existing detectors. And then I also showed a difference between the Blem's triangle and the Migdal effect. And interestingly, the range we are interested, actually the Migdal effect dominate the events. And currently we are discussing the possibility to see the Migdal effect using the neutron source. So thank you very much.
I assume everybody's clapping. Thank you very much, Taro.
Thank you.
So I see people have raised hand already. So Luca Grandi.
Hello, hi. So I have a question related to the following thing. So in one case, when you have a pure elastic recoil and there is not this component, you have a nucleus that is neutral and recoils, okay? In the second scenario, you have something that is not neutral, right? Like it's an ion or can end up into being an ion. So in your calculation, I think you consider that the response of a detector to an ion, so to a recoiling ion or to a recoiling neutral atom is the same. But I don't understand if this is just an assumption or not, because in principle, you know, I can imagine that an ion is much more ionizing, for example, than a neutral particle.
I mean, sorry, maybe there's some parts just I couldn't hear. So, so you basically.
Yeah, I'm wondering, so you have two processes that you consider. First, the pure nuclear recoil, and let's say that is without the Migdal effect. Okay?
Yeah, right.
And that would be just the nuclear atoms that recoils into the medium, right? It's not charged at all.
It's just ordinary scattering with dark matter. I mean, with the dark matter nucleus scattering, right? Just
yes.
Using the some interaction like a weak force or something like that. That is usually we assume for the dark matter scattering.
Yeah, no, that is clear to me. But in that case, you have the entire atoms that follows the nuclear recoil, right? You have a cloud of electrons
right.
that follow the nuclear recoil. So in
All
that
over
case,
the
something that is neutral. Then now let's put apart this case and let's take the case of the Migdal effect that you mentioned. In this second case, you end up having some energies that go into electrons and some that is leading to an ion, right? Something that is charged. So it's no more a neutral object that moves, but is an ion that moves plus some other energy that goes into the electron channel. So my question is, in xenon, in a xenon medium, maybe the response of liquid xenon to an ion is different from the response of xenon to a nuclear recoil. While my impression is that in your treatment, the only difference between the two cases is the fact that you have some energy that goes into electron in the second case. But in terms of what happens to the nucleus, you are treating them in the same identical way, as if they were both neutral. So I'm wondering if that is an assumption, or if you think that calculation shows that an ion and a neutral nuclear recoil should produce the same thing.
Actually, that is assumption, but actually, I think that the assumption is not so bad. First of all, the nuclear recoil, we calculate the sum of the electron and the emitted photon, and also the nuclear ion. But actually, almost all of the energy is the photon and the electrons, and just a little energy just goes to the kinetic energy of the ion. So in that sense, yeah.
But then when you say that the impact of the component that is electronic related is much larger than the one that is associated to the nucleus moving, then you are assuming somehow that what we know from recoils of neutral nuclear recoils is the same in the case of ion, because maybe even if you release very little energy into the ion being charged might be much more ionizing than your regular nuclear recoil. And that might lead to a term that, despite the low energy, might provide an extra amount of electrons, and so not being so negligible with respect to the electronic part of your process.
Luca,
right, yeah.
I think Yutaro answered that they don't calculate that, and this is indeed a lot more difficult to do that in the liquid xenon, right? This is a secondary effect. But I would like to ask also something about that, but unfortunately for me, I see there are raised hands that are not me. So I will let them ask their questions. Look, I'm sorry that I'm cutting you, just that
Okay.
we have 4 people already. So let's start with Laura, then Manfred, and then Uwe.
Okay, hi. Yeah, I just have a short question on your first method that you proposed, because you already give neutron flux and thresholds. So did you look at the backgrounds that you would see in the detector, that are not related to the neutron source? I mean, what do you mean slow? So I guess, first of all, it is a pulse source. So you look at the events that are in coincidence with a pulse source, so that you can reject some of the background, or because it seems to me a very low neutron flux, 10 to the 3 per square centimeters and per second. So I would expect that your background, from other sources would be much higher. But yeah, that's why I wonder if you looked at this.
Actually, it's just I calculated yesterday. I brought this figure yesterday. I just don't consider any background. Actually, I used this flux from the other experiments. This one. Actually, we are discussing about this, and I know that the actually we have this source flags. I have defined to have this source, so I use this as a example, but this is just there for
Okay.
so you can just
Yeah. Okay, thanks. Yeah.
Okay. This is what you're working on with Shingo?
Yeah.
Okay. This is for us experimentalists to see what's the background, as usual.
Yeah, Shingo will know, I'm pretty sure.
Yeah. All right. Now, who we said is next? Manfred.
Okay, hi. Nice talk. My question goes in a similar direction as Lucas, I say. I think there's two levels of the discussion. One is to argue that the whole atom forms a recoil, which is, I think, in a certain sense, a naive picture because there is ions and not full atoms, etc. and so on. But there's yet another direction, namely the electronic levels of xenon in a liquid are not identical to the electronic levels of a xenon atom by itself. Inter-atom forces in xenon are very strong, and you can see that because the surface of a xenon liquid is extremely different than the inner part. That's, by the way, why xenon is a very perfect cleaning liquid. So can you estimate these effects, how big the change of the dynamics and the levels of the electrons in the xenon liquid impact the calculation?
Not completely. That is completely next work. It's a very very difficult problem. And yeah, of course, we need to prepare some wave function like something of the liquid state of the atom. So maybe we can, but we are now not. We had not calculated that point. That calculation.
Okay, thank you.
Okay, and Uwe?
Okay, yeah, so also thank you for your talk. Looking at the slide that you have up there right now, I was wondering, so if I now come in with, say, a 30 keV pulse neutron source or something that has as maximum at least something like that, and I would now try to measure what comes out. So then I would see a spectrum, or would I see just a continuum?
30 kV is, I think it's just, I mean, it comes from the outer shell electron goes to the most inner shell. And it's, the binding energy is fixed, so it's just a line.
I think he's asking about the incident neutron at 30 keV, not the gas X-ray, but this one, the one that is on the slide currently.
That's right.
This one?
Yeah, the one you're showing now, yeah.
Yeah.
So assume I have a 30 keV neutron. I somehow know by that my pulse.
Thank you.
So assume I know I come in with a 30 keV neutron. What is the expected, and I select only those, and now I collect a spectrum. What is the spectrum that I would expect to see in the detector?
Spectrum of the
So is there some part is continuous? Is there some lines on top, or?
It's just like the these. I think these are still like this figure. It's just it depends. It emits the electron, so it's continuum. So just like this. So electron. If the electron energy becomes larger, then it's just less probable. So, and we need some energy to excite that state. So we have this. So this may be the same as it. If you do some experiment on this, then you will observe this kind of distribution.
This was fairly high energy, right? I mean, for this neutrinos.
For the neutrinos.
If you go back to your neutrino plot, I didn't understand what you wanted to show me there. So.
This is neutrinos, but basically the shape is the same. Yeah.
So for a line, for a neutrino line source, or for a continuum, I'm assuming I really have a monoenergetic neutron source right now. So this is for which one, the beryllium or?
None of these are monoenergetic. They are spectra.
Well, beryllium would be, but I think it's for the Bohr. That I understood that it's for Bohr 8. So the
Bohr 8, yes. Only these two.
Yeah.
So okay, so that is a continuum. So that's not an answer to my question. My question is for, assume you had a pip neutrino, right? That would be the equivalent. So the PEP, or so I come in with a monoenergetic source. What is then the spectrum?
The monoenergetic case, it's also continuum because it's just it depends on the angle, scattering angle. So.
Yeah. Okay. I can fix that.
If you fix the also the angle, scattering angle, then wait, then so it's just maybe it's not completely line. I think that some of the energy just goes to the kinetic energy of the atom, and some of the energy just goes to the energy of the electron. So we can choose that how the rate of the energy distribution. So I think that still have some width.
Okay. I think if one could compute that, that would be an interesting plot to see, I think. Okay. Anyway, thank you.
Yeah, thank you.
Thanks. I have 1.5 questions. So first of all, related to Luca's question, if you can go back with one of the earlier slides, you calculate the probability for an ionization or excitation. Let's focus on ionization of the most shallow, the most shallow shells. So they are quite probable to be excited, to be ionized, right? So if you give energy of, now you're talking about relatively low momentum transfer. Let's say you're talking about momentum transfer that is relevant for, let's say the classical WIMP, that our recoil energy of, let's say 10 keV. What would be approximately the probability to ionize an outer electron, so an electron in one of the outer shells? N equals 5. Is this approaching 1, or is this a rare event?
It's N equals 5 to. yeah, and I mean the integration of this just gives this and that. Actually, outer shell is easily excited, and actually you can maybe see.
So here you take the QE of ME times 10 to minus 3, but if you take that much higher, I'm just wondering if maybe what we always look at when we look at the nuclear recoils is always Migdal that leaves us with a non-neutral ion recoiling.
And that may be interesting if the ionized atoms is important, because actually outer shell can be easily ionized, and in this just scale that's QE squared, and at that point this is approximation just blocks down, because this is the expansion of the QX, and the QX becomes larger than 1, and this cannot be used. But actually the rate becomes very large, and but actually it's outer shell, so it's maybe just part of the wave function of the other atoms. So
it's hard to
know
calculate, but
in the real calculation, in the real system, what is happening? I don't know what is happening, but if it's isolated, then it's very probable to excite ionize the most outer shell. But in the
so xenon in vacuum, a xenon atom in vacuum would be typically ionized by a nuclear recoil of, let's say, 10 K.
I think, but actually, I need to calculate more higher order, but
okay.
I don't know. But
for us, it might
maybe
be an
the second
question, but it might be. I'm not.
Yeah, and in the outer shell, the x is roughly the size of the outer shell, the radius of the outer shell, and even in this calculation, it is in the outer shell that this approximation is not so good. So, yeah.
Okay.
Rani, if I understand it right, you mean that the normal nuclear recoil, basically part of the energy comes just from the ionization of this outer shell electrons. They are so very small in energy that they will contribute to the main one.
The energy might be negligible.
Yeah, right. Binding energy is very electron volt, and the emitted electron is also very small. I think that it's less, say, the electron volt also. So it's completely.
So you can get 15 or 20 EV in it's electron recoil now, because it's not really recoil. But what you get is not a neutral xenon atom in liquid xenon, but you get already an ionized atom from the initial kick.
Right, but actually there are many other atoms, and even the emitted electron is, say, the 10 electron volt or so. So I don't know what happened.
No,
so it may be emitted, but it's just to capture other electrons. So I don't
know. Okay, that's an interesting thing to think about. I don't know how, but it's interesting. So if anybody else has a question, you can wave or just unmute and ask, because I don't see anybody.
I have one. I don't know how to wave my hand.
I don't know if you can.
It is just very, very naive. Is this effect already observed and measured with other atoms? For example, you you brought the calculation, the theoretical calculation with hydrogen, but there were already some, let's say, experimental setup that measure the contribution of this effect to cross sections.
You mean for this? I mean, it's actually to measure this effect, we need a very low energy neutron source, and actually, I don't know the such experiment. So if there is some experiment that measures this effect, then it's very nice. But so far, I have not found any such paper.
Okay, thanks. Because as experimentalist, I was always surprised that, well, not. I mean, I always read that this is a very well-known theoretical contribution to the cross-section, but well, I just tried to find some paper that tried to measure it, but I have not found it. So it seems that probably it's very difficult to measure.
Yeah.
Okay.
I have one. Oh, sorry. Can I still ask? So somehow the bottom line of what you have presented, including also the neutron scattering and the current neutrino, it seems like that the bullet that you use does not really matter. What matters just the energy transfer. Is this naive interpretation correct?
You mean the matter? You mean the target or
Yes, sure. The target matters, but when you use a bullet, it can be a neutron, a WIMP, or a neutrino, and what it matters is just how much energy transferred to the target.
Yeah, it's like it's just how much that particle just deposit the energy. If there is some coupling, then that's enough.
Okay.
Thanks a lot.
Okay, so thank you very much again. And I learned a lot and I enjoyed it. So it was a very good thing. And have a good night in Japan. All right, we can clap. I think whoever is able to clap over there. And thank you very much. Okay.
Thanks a lot.
Bye-bye.
Shoji-san.
Hi.
Yes, I'm Yamashita. I just joined Nagoya group from this April. I'm working on Xenon experiment.
Oh.
Nice to meet you. So maybe we see at
Nice to meet you.
Thanks for talk.
Thank you for joining this. Seminar.
Joy, I just have a quick comment to when you do, it's not a question, it's just a comment, when you do the simulations of what you would expect in a small detector, but I'm sure Shingo is well aware of that. I think a problem that you're going to run into is that your detector is a finite size and it'll have a position dependent light and charge collection efficiency, which means that the energy threshold is position dependent. And now the thing is, I think I've not done this, well, I've done back of the envelopes, but I haven't really done a simulation. But I think a problem to be aware of is because you have this many orders of magnitude in difference between the electronic recoils and the Migdal effect. I think what you need to make sure is that you build a detector and you tune your neutron energy such that in those parts where the detector functions really well, your rate of electronic recoils is still so low that you don't, because right now the plots that you have, they drop off very sharply.
Yeah, right. So
dependent threshold, this will become very smeared, and so I think it'll be
hard. I agree. Yeah. So we need so large enough structure than the small enough neutron system. Maybe. But this is just you're just theoretical side.
No, of course.
So, yeah,
but
I will discuss with the other people later. Maybe I just come out with this when I'm making this slide. So.
Raphael, he's a theorist. You shouldn't worry about that.
But actually, at that high energy, are you able to distinguish between the Migdal effect and the bremsstrahlung?
Oh, that's a good question. Actually, under that high energy case, actually, the bremsstrahlung may be larger than the Migdal effect. But actually, I should say that two effects are almost the same. I mean, whether the both of the, I mean, I should show this. Yeah, both of these processes start with the emitting the photon from the nucleus. And that photon is if that photon is completely captured by the electron, and then it's the Migdal effect. But if that electron is first absorbed by electron, but then it emits electron, photon, then it's a bremsstrahlung. So I think in the high energy limit, these contribution seems to be the same effect.
So from experimental side, we can only say Migdal plus bremsstrahlung.
Right.
Unless you
and
have
the process is almost the same. Yeah.
But if you get an actual let's say K-shell line like the 30 kV,
right? Yeah.
That is not bremsstrahlung because the bremsstrahlung is going to.
Yeah, right. That's right. Yeah, that's correct, Andy. Yeah. The Migdal effect, we use the atomic structure. Yeah. So bremsstrahlung is just not a line, but just a distribution. And that's different.
Taro, I have to leave. Thank you very much. I really enjoyed it. Okay.
Thank you.
Bye.
Thanks a lot. Bye.
Can I ask you something before you disconnect?
Yeah.
Me or?
No, yeah, you, Taro. Yeah. So you're modeling the nuclear and the electron waveforms using Hartree-Fock, right? And then you have this like 20% uncertainty in the energy.
Right.
Yeah. So my question is this a good enough model? Do you have any plans to improve like the precision in the modeling of nuclear and electron waveforms, or this you think compared with other uncertainties that you're dealing with is not like a key factor to keep improving?
Actually, this is just my one, but actually. First, we want to see the Migdal effect. So
yeah,
that's the first step.
Me too.
Yeah, we can basically improve the precision, and the I actually don't calculate which is the most uncertain things, but yeah,
Mm-hmm.
I think the electron wave function is one of the largest uncertainty.
Yeah,
And
yeah.
then,
Usually, is
yeah,
is the
I
case.
also compare the oscillations, oscillator strengths,
Mm-hmm.
and then I remember that it depends on the state, but maybe older one uncertainty seems to be there. So,
So you think it's better to wait until you see it experimentally before thinking how to improve the modeling in the nuclear and electronic? Yeah, that makes a lot of sense, actually. Yeah.
Yeah. That's my plan, but maybe other people may be thinking of the improvement part.
Yeah, thank you.
So I'm afraid that if I leave the meeting, I'm the last host, it will be closed. Is there any other, otherwise I will cut you, that's why I'm still here. Do you have any other question or we can close it? Okay, I think we can. So I want also to thank you very much for your talk and your explanation. And I think this generate a lot of interest. I'm pretty sure that we will stay in touch also with Shingo in the same group as you, contact as you. Okay, bye-bye. So I close the meeting.
Bye-bye.